Network reduction techniques. In that we have four types of network reduction techniques. One is series circuit, next one is parallel circuit, third one is series parallel circuit, and fourth one is star to delta and delta to star transformation. In that first is series circuit. The series circuit means it is a circuit in which two or more resistors are connected in series. Means here in the series connection it is an end-to-end connection. See, the resistor of the first resistor of the second end is connected to second resistor of the first end, and this second end of the second resistor is connected to first end of the third resistor. Means this is the end-to-end connection. So in any circuit, if two or more resistors are connected in series, then the circuit is called series circuit. So in the case of series circuit, the total resistance is R1 plus R2 plus R3. If we are connected in resistors in series, then the total resistance is R1 plus R2 plus R3, so on Rn. Next, the characteristics of series circuit. So in the case of series circuit, the current across each resistor is same. If you have connected N resistor, then the current in N resistor is same. That is I1 is equal to I2 equal to I3 equal to so on In. That value is I only. And the supply voltage B is the sum of the individual voltage drop across the each resistor. See, in this circuit we have the three resistor. So across three resistor, the voltage drop is different. That is V1, V2, V3. So the sum of these three voltage drops is equal to the supply voltage. If you are connecting the N resistors, means V is equal to V1 plus V2 plus V3 plus so on Vn. Next, similarly, in the series connection of resistor, if the two or more inductors are unconnected in series, then the circuit is called series connection of inductors. Then in case of the equivalent inductor is L1 plus L2 plus L3. And series connection of capacitor, if two or more capacitors are connected in series, then the total capacitance is 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. If you are connected n number of capacitors in series, then the equivalent value of that capacitor is 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on 1 by Cn. Next, parallel circuit. Parallel circuit in which resistors are connected such that one after the other or one over the other is called parallel connection of circuit. See in this diagram here, the three resistors are connected in parallel. Means each one end of the resistors are connected at one node and other end of the resistors are connected at one node. So this kind of connection is called parallel connection of resistors, and the characteristics of parallel circuit is in case of parallel circuit, the voltage is same across each resistor. There is a voltage drop across each resistor is same, but the current is going to be divided because see here we have the two terminals. So at these two terminals, the voltage is same because the input voltage should be equal to the output voltage. So that way the voltage is same across each resistor, but the current is going to be divided. So the characteristics are the voltage is same for each resistor in a parallel circuit because there are only two electrical common points and the voltage between that common point is always same. So that is V is equal to V1 equal to V2 equal to V3 so on Vn. If you are connected in number of resistors, then that is the total n number of resistors are same voltage drops. Next, the electrical current can be the total current is equal to the sum of each branch individual currents. That is I is equal to I1 plus I2 plus I3 plus so on up to In. So the R equivalent in the case of parallel connection of resistor is 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So in the case of inductors, if three inductors are connected in parallel, then the equivalent inductance is 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. Similarly, in the case of capacitor, if the two or more, here in the circuit we have four capacitors are connected in parallel. So the total capacitance is C equivalent is equal to C1 plus C2 plus C3 plus C4. So in this tabular column, we have different devices, that is the different parameters, resistors, capacitor, inductors. Then if the resistors are connected in series connection, the R equivalent is R1 plus R2 plus so on Rn. If n number of capacitors are connected in series, then the equivalent value of the capacitance is 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus so on up to 1 by Cn. If n number of inductors are connected in series, then the L equivalent is equal to L1 plus L2 plus so on up to Ln. So in the parallel connection, the equivalent resistance is 1 by R1 plus 1 by R2 plus so on 1 by Rn. In case of capacitor, in case of parallel connection of capacitor, C equivalent is equal to C1 plus C2 plus C3 plus so on Cn. And in case of parallel connection of inductors, the L equivalent is 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus so on 1 by Ln. So see, in this example here, we have resistors are connected in series and parallel. So this is the example for the combination of series parallel connection of resistor. So in this circuit diagram, we want to calculate the R equivalent. So for that, first always we have to calculate the equivalent resistance where the circuit is closed. So this side is circuit is closed. So see from this side. So here the 4 ohm, 5 ohm and 3 ohm, these three resistors are in series. So the total resistance here 4 plus 5 plus 3, that is 12 ohms. Now the circuit becomes like this. So in this case, here the 12 and 4, these two resistors are in parallel. So here the total resistance is 1 by 4 plus 1 by 12. So that value is 3 ohms. Again, this 3 ohm and these 3 ohm are in series. So directly we can add these two resistors. So 3 plus 3, that is 6. And next the remaining circuit is like this. So here again the 6 ohm and 6 ohm, these two are in parallel. So 1 by 6 plus 1 by 6, that value is 3. Now our circuit becomes like this. So here this 4 ohm, 3 ohm and 3 ohm, these three resistors are in series. So the equivalent is 4 plus 3 plus 3, that is 10 ohms. Next, we have current division rule and voltage division rule. See, this current division rule is used to analyze a parallel circuits, and this voltage division rule is used to analyze a series circuit. So here, see in this circuit diagram, here the two resistors are connected in parallel. So here the source supply is Vs, that is source voltage is Vs, and here the current is Is. And at this node, the current is going to be divided. So across R1, the current is I1, and across R2, the current is I2. So if you want to find the current across each resistor, then the formula is I1 is equal to, so to find here the I1, I2 current, we are using the current division rule. So the current division rule is total current into opposite branch resistor by sum of the resistor. So if you want to find the current I1, the total current is Is, and opposite to this I1 current, we have the resistor is R2. So R2 by R1 plus R2. Similarly, if you want to find the current through resistor R2, so I2 is equal to total current Is into opposite branch resistor, that is R1 by R1 plus R2. So this is about the current division rule. Next, voltage division rule. This voltage division rule is used to analyze the series circuit. So in the case of series connection of resistor, we know the current is same, but the voltage drop is different across each resistor. So if you want to find the voltage drop across each resistor, then we can use this voltage division rule. So this here, the V1 is the drop across R1, and V2 is the drop across R2, V3 is drop across R3. So to find the V1, we have the voltage division rule, that is the total voltage into same branch resistor by the sum of the resistors. So here V1 is equal to R1 by R1 plus R2 plus R3 into Vs. Similarly, drop across resistor R2, that is V2 is equal to R2 by R1 plus R2 plus R3 into Vs, and V3 is equal to R3 by R1 plus R2 plus R3 into Vs.